Good morning, good afternoon, good evening, depending on where you are from, and a very warm welcome to today's FEA Academy webinar. I'm Dominique Madier, founder and director of FEA Academy, and I'm delighted that you've chosen to spend the next hour with us. And what I strongly believe is one of the most high impact topics you can invest time in as an FEA engineer. Before we get into the substance, let me take 2 minutes on housekeeping so we can all get the most out of this session. The webinar will run for approximately 60 minutes, and I leave the final 3 minutes for your questions. So please do save those for the end. So you see there is a section, the Q&A. I'm pretty sure you know that, the Q&A panel. So put your questions there during my talk, and I will go through them at the end. This session is recorded, so a replay link will be available on the FEA Academy YouTube channel within approximately 48 hours after the live. Okay. And on top of that, the SOP starter kit will be available also as a PDF that you will be able to download from the FEA Academy website after the session, and for sure you will receive the link in your email box after the webinar. As I said, the Q&A panel is your friend. Ask the question and I monitor it. Before to jump to the agenda, a brief word on who I am and why you might trust anything I say on this topic. I've spent over 2 decades, more than 2 decades now, doing FEA in demanding industrial environments, primarily aerospace, where getting it wrong isn't a rounding error, it's a safety event. Over those years, I developed a real obsession with model quality, not just whether the physics is right, but whether the process that produced the result is traceable, repeatable, and defensible. So FEA Academy grew out of that obsession, exactly that obsession. And my goal is very simple, to help engineers everywhere do better FEA. By that, I mean more consistently, more rigorously, and with greater confidence in their outputs. It's because it's not easy with FEA. So as you know, I post regularly on LinkedIn on these topics. And if you find today useful connecting with me, there is the best way to stay in the conversation. Okay. So let's jump to the agenda. Here is what we are going to cover. I've structured the session in a deliberate sequence, starting with the business case, okay? Then the framework, and then going deep, on each stage, and closing with the practical implementation guideline. It is pretty much the agenda. The reason I do in this order is important. If you don't believe in what SOPs matter for FEA, you won't have the internal conviction, to make them stick. So we start there. So let's begin at the beginning. Why does this matter? Let me start with a question, and I want you to answer it honestly, okay, in the chat, even if only to yourself. If 2 of your analysts independently build an FEA model of the same component, it's very important, the same component, same loads, same material, same geometry, and run it through the same solver, how different would their results be? Okay, answer that this in the chat, please. No, it is the same component, the same exact model with the same solver. I would be curious to know how different do you think would their results be? So I see different, about 5%. Hopefully the same. The stress and displacement location would be different. might be very different depending on assumptions, boundary condition, etc. About 3 to 5%. Okay, so we have very different visions, opinions there. That's very interesting. The uncomfortable truth is that for most engineering organizations, the answer is meaningfully different. Not because the analysts are incompetent, it is not. They aren't, okay? Not because FEA is unreliable, it isn't. But because the process has no standard, okay? The results depend on the analyst as much as it depends on the physics. And that is a fundamental quality problem, okay? Absolutely, Remo. Very different depending on assumptions, load boundary conditions. Totally agree with you. So, why SOP matters in FEA, okay? There are 4 pillars. Let me give you a specific first about the first pillar, error prevention. Let me give you a specific real-world error type that SOPs directly prevent, the silent unit error. An analyst import a CAD model exported in millimeters into a solver configured for meters. The geometry looks right, okay? Dimensions are off by a factor of 1,000, but visually it is the part that the analyst is expecting. Let's say it's a bracket, okay? It looks like a bracket. The mesh is generated, the loads are applied, the solver runs, and the results, stresses are 1 million times too small. If you're not checking units, which most people don't explicitly every time, it's a disaster. So a unit consistency SOP, 3 lines, a checkbox, eliminates this class of error definitively, forever. Okay? Let's jump to the second pillar, the team consistency. So from the previous example, now scale that unit error scenario across a team of 10 analysts, each with their own CAD import edits, their own favorite mesh settings, their own interpretation of what adequate convergence means, and you don't have a team doing FEA. You have 10 individuals doing FEA. So the variation in results is a measure of process noise, not physical reality. So SOPs compress that variation. They move the baseline up, not by constraining the good engineers, but by ensuring the minimum standard is visible and shared. Okay? The third pillar is the review efficiency. Here is something I observed consistently. When the deliverables are standardized, there is a standard in the deliverables, review time drops by 40 to 60%. Not because the reviewers work faster, but because they don't have to go looking for things. The mesh quality report is always in section 3, for example. The free body check is always on page 7. The acceptance criteria are always in the executive summary. Standard in, standard out. And the last pillar, the fourth one, is confidence and trust. And it's very important, okay? The most commercially significant benefit here, the pillar 4. In regulated industries, your FEA must be auditable. In commercial environments, your results must be trusted by clients who didn't run the analysis themselves. The SOPs give both groups the same thing, a documented, traceable process that can be interrogated and reproduced. So an FEA report from a team with SOPs reads differently. It answers questions before they are asked by the customer or the authority of certification. It documents what was assumed, what was checked, and what was decided. That confidence is not just engineering, it's a competitive differentiator. Okay? So now we are convinced that SOPs matter. Now let's look at exactly where in the FEA process they need to live. I want to introduce a framework that I use in all my FEA mentoring and coaching work. It's deliberately simple. 6 stages, because simplicity is what makes a framework actionable. A complex frameworks get studied. A simple ones get used. So the 6 stages are, first, the stage 1 is model creation, geometry, idealization, coordinate system, file management, stuff like that. I will come back in detail on each stage. The stage 2 is material data, the library management, the traceability, the validation of the material data. The stage 3, loads and boundary conditions. By that, I mean the load cases applied on the model, but also the constraints. The stage 4, meshing, the element selection, the quality metrics, the convergence, the mesh size. The 5th one, the stage 5, is solving, for sure. At the end of the day, we need to solve the solution. So we have the setup of the solver, the pre-run checks, the convergence monitoring during the solving. And the stage 6, the last one, is the result interpretation, extraction, acceptance criteria, the reporting. So here you have to think of these 6 stages as a pipeline, not a checklist, a pipeline, okay? And it's important because by the pipeline, this analogy, it means that each stage feeds the next. Contamination introduced at stage 1 propagates through every subsequent stage. A wrong unit system, for example, if I come back to the example at the beginning, a wrong unit system in model creation doesn't just affect the model, it affects the mesh size, the load magnitudes, the solver tolerances, and so the results, okay? The error compound. And this is why SOPs must exist at every gate, not just at the output. A Q&A check at stage 6 cannot catch an error introduced at stage 1, okay? You need upstream intervention. So let me give you a quick orientation of what each stage entails before we go deep on each one. The stage 1 in model creation. This is where the geometry enters the FEA world. Decisions made here, what to simplify, what to suppress, what coordinate system to use, set the foundation for everything. A bad idealization decision at this stage, at the first stage, cannot be rescued by a better mesh, at the stage 4. The material data. The material properties you assign define the stiffness, the strength, the failure behavior your model will predict. This is also one of the least controlled stage in most organizations. Material code copied from an old model. I see that every time. Properties used outside their validated range, or even the sources undocumented, okay? At the stage of loads and boundary conditions, this is where physics enters the model. It's also where the most consequential engineering judgments are made and where the most dangerous errors hide. Because a wrong boundary condition can produce a plausible looking but completely wrong result. At the stage 4 meshing, as you know, the mesh is your discretization of a continuous problem. It is the backbone of the finite element method. its quality governs whether the physics you've set up in stage 1 and 1 to 3 is correctly captured in the numerical solution. So a good mesh is not just fine, it's appropriately fine in the right places with the right element types. Very important, okay? By meshing, it's not only creating the discretization, it's also selecting the right element. The stage 5, the solving, this is where the numerics happen. Most engineers treat the solver as a black box, okay? Press go, get results. SOPs for the solving stage ensure you go in with a pre-flight checklist and that you monitor for suspicious behavior and come out with a verified set of results before you even look at stresses. And finally, at the result interpretation level, what do the numbers mean? This is the stage most vulnerable to cognitive bias, confirmation bias in particular. SOPs here enforce predefined acceptance criteria, standard visualization, and explicit documentation of what the results can and cannot be used to conclude. So let's go deep now. We're going to spend the next minutes working through specific actionable SOPs for each stage. The stage 1, the model creation SOPs. The model creation is deceptively complex, okay? Engineers often treat it as a mechanical task. They import CAD, they clean up, and move on. But the decisions made at this stage are irreversible. You cannot change them in practice because by the time you have a mesh, hundreds of downstream decisions have been built on top of the geometry and on top of the mesh. So the core of any model creation SOP is a structured idealization, okay? I should say is a structure idealization decision record. Before any geometry enters the FEA environment, the analyst must document what has been simplified and why during the cleanup process. You see what I mean? Which features have been suppressed and what their stress contribution is estimated to be and what the approval status is. This document is signed off before meshing begins, not after. And why the sign off before meshing? Before, once you've spent 4 hours meshing a complex assembly, the psychological cost of going back to fix the geometry is huge. So the sign-off gate enforces the right sequence. Also, the coordinate system, it is the invisible source of errors. The coordinate system errors are the FEA equivalent of left-right confusion in surgery. They are silent, they are common, and they can invert your stress result completely. And believe me, the SOP is very simple. Define the global coordinate system at project kickoff. Document it in the analysis plan and review it as the first item in every peer check. And the same for the local coordinate system. Document them, define them in advance. Okay? So take time to scan this SOP table covering the stage 1 model creation SOP. So now the stage 1 gets the geometry right. The stage 2 gets the material rights. And I want to make a bold claim about material data. And I want you to take it seriously. In most engineering organizations, the material data management process is broken. Not imperfect, broken, or doesn't exist. Here is what I typically find when I work in FEA with my customers. The material cards that have been copied from model to a model from years, from model to model, okay, with not one able to trace to trace them back to a source document, okay? The properties are used at temperatures well outside the validated range with no flag, no warning. It's very common to see that. The proprietary material cards where the original test report no longer exists or was never linked in the first place. It's very, very common to see that. And this matters, you know what? Because material errors are non-conservative in unpredictable ways. A mesh error will usually make your results conservative. Your stresses are too high. You add margin, okay? A material error can go either way. You might be under-predicting the stiffness and missing a resonance in a frequency response and model analysis. You might be over-predicting the strength and missing a failure mode, okay? And you're going to fail a test, definitively. So the fix is very easy. It is a centralized version control material library with 4 mandatory fields for every entry: the property value, the source document, a datasheet revision, test report number, or applicable standard, and the validated temperature range, okay? And the date and the author of the last review. So the access to add new entries is restricted to nominated data person. It's very important. It's not an open database. All users can read, but not all users can write. So, just a quick question in the live: is anyone already running a structured material library? Drop a Y in the chat if it is the case. I am curious to know how common this is. Ryan say somewhat. Okay, it's not something official, right? No from Ryan. And you know what? It's common. Most of the customers I'm working with, they don't have one. Okay, I have to work with them in order to help them putting something together, okay, in order to have something very, very robust. So our geometry is right, our materials are right. Now we need to tell the model what forces to apply and how it's constrained. So it is the laws and boundary conditions, SOPs. The laws and boundary conditions are where the physics of your problem interfaces with the numerical model. There are also the area where I see the most engineering judgment applied, which means they are the area most in need for a documented paper trail, okay? The most common BC error is not a mistake in a load magnitude. It's a conceptual error in what the constraint represents. I have reviewed analyses where components were bolted to the ground in the FEA model, where in reality, they were bolted to a flexible substructure. And I'm pretty sure you too, you have seen that. The physical stiffness, in that case, was orders of magnitude different from the model stiffness. Obviously, the results looked fine. The physical test told a different story. You understand that? So the SOP answer: every constraint must be accompanied by a written statement of what physical behavior it is intended to represent, and a qualitative assessment of the sensitivity of the results to that assumption. And it is not optional. It is the engineering rationale for the model. And it's very simple to put in place. So the load sign-off is a non-negotiable gate. All the load data, the magnitudes, the directions, the application points, the combination rules, because we combine some effects, must be signed off by the responsible structural engineer before any analysis run is submitted. and not after, not informally, a written record with a date and a signature. It's very easy, you know? And the reason is simple. Load data is the entry point for requirements. If the laws are wrong, every downstream result is wrong, okay? The sign-off gate ensures that the bridge between the requirements and the model has been reviewed by a qualified engineer, okay? Now, with geometry, materials, and loads defined, we are ready to discretize. Let's talk meshing. Meshing is the stage that most engineers associate with FEA skill. And skill is still for sure required. I agree with that. But skill without standard is inconsistent. Your mesh quality on Monday morning is different from your mesh quality on Friday afternoon before a release deadline. Okay, so very important. The choice of element type is not a software default. It is an engineering decision with real consequences for accuracy. Okay, shell element versus solid elements for a thin wall structure. The correct answer depends on the wall thickness, the stress gradient, and the result you're trying to extract. This decision must be documented and not assumed, and it has been managed by the stress analyst and the FEA engineer. The mesh quality metric is setting your thresholds. Okay, every organization needs to define its own quality thresholds, appropriate to its typical analysis types, element technologies, and solver. So here, what I recommend as a starting point, it is that aspect ratio less than 5:1 for shell element in regions of interest, the skewness below 60 degrees, the warpage below 15 degrees for shell elements. But be careful, these are not universal. They are starting baseline. Your SOPs should define what is appropriate for your context, your solver, and the type of analysis you are performing. The critical discipline, before any analysis job is submitted, a mesh quality report must be generated, okay? Reviewed and archived. Not checked mentally, generated, reviewed, archived. This creates an auditable record that the quality check was performed. And between you and me, it's very easy to do. With the modern pre-processing software we have, it's a click, a simple click. As soon as the criteria are defined, okay, and recorded into the pre-processing software, it's one click, and you have the big picture. You save and you put in the documentation. Now, the last point about the meshing SOP, it is the convergence study obligation. I'll be direct here, okay? A mesh convergence study is not optional for any structural analysis where quantitative results are used to make the design decisions. I know convergence studies take time. I know that. I make a lot of them. I know programs have setups, but if your results haven't converged, you don't know what they mean. And you certainly can't use them to justify a structural decision. So the practical SOP, pre-mesh density, minimum, okay? You plot the key output quantity against the element count in order to have your convergence curve. If the finest mesh is within 5% of the medium mesh, you've converged. You document it, you archive the convergence plot, and move on. Okay? The mesh is built, the model is complete, time to solve. And the solving stage has more to it than pressing go. Okay? As Jones say, convergence study for bigger model is tough and time taking. I completely agree with you, Jones. It is not an activity you do in few steps. It does not take few minutes. It's few hours. Yeah, I agree with you, but you don't have choice. So let's deep dive in the stage for solving SOPs. The solving stage is where most engineers stop paying attention. And you see what I mean there. And where some of the most damaging silent failures occur. The solver runs overnight. You come in the morning and you see solution complete, and you go straight to the post-processing. That is not an acceptable workflow. Here you have the pre-run checklist, your pre-flight process. Every pilot runs a pre-flight checklist before takeoff. No matter how many times they've flown the same aircraft, okay? The pre-run checklist for FEA serve exactly the same purpose. Before every job submission, the analyst must complete and sign the checklist. And it's very easy. I can even share with you a checklist, okay? A complete checklist. The key items, the model total mass, okay? Does it match the end calculation? The degree of freedom count, is it reasonable for this model? The free body balance, do applied forces and moments sum to zero? The estimated runtime, are we expecting hours or days? These checks take 15 minutes. They catch, in my experience, approximately 30% of significant analysis errors before the solver even runs. Also, you have to define your convergence criteria before you run, not after. For a nonlinear analysis, specify the force residual norm, the displacement norm, and the energy criteria. For a linear analysis, check that the reaction forces balance the applied force, the applied load, sorry. Check also the residual error. It should be very, very small. And here is a rule I enforce absolutely. No result may be accepted if unexplained critical warning exists in the solver log. Yeah, you have to read the solver log, okay? And every warning must be reviewed and understood. Every warning must be educated, either explained and documented as acceptable or corrected. No exception. This single rule, has caught more significant model errors in my career than any other practice. So the solver has delivered his verdict. Now comes the intellectually demanding stage, and the one most vulnerable to bias, result interpretation, the last stage, okay? Here at this level, the results interpretation SOPs, I want to start with a principle that I consider, again, non-negotiable, and which I want you to take away from today, even if you forget everything else. Acceptance criteria must be defined and approved before you look at the results. Not during, not after, before. I said that because if you define your acceptance criteria after seeing the results, you are not doing engineering. You are doing post hoc rationalization. You may feel like judgment. It is bias. The SOP enforces the right sequence by requiring that acceptance criteria appear in the signed analysis plan, which is approved before the run is submitted. There is the case also of result extraction standardization. How you extract the results defines what you compare. If one analyst averages the stresses across element nodes and another uses the unaveraged element centroid value, their margin of safety calculations will differ for sure, okay? Not because the physics disagrees, but because the extraction method disagrees. So to standardize the extraction, again, document it. Make it the same for every analyst on every project. I will conclude this deep dive of stage 6 by the deliverable package, your evidence base. The final output of any FEA project is not a number. It is a documented evidence base. The model, the mesh quality report, the convergence study, the result plots, the acceptance criteria comparison, the peer review checklist, and the sign-off record. This package is what permits someone else, a peer, an auditor, a future engineer, to understand, reproduce, and trust the results. Okay, so SOPs define the contents of this package. Every item on the list is mandatory. No item is optional because the schedule pressure, for example, okay? Or because someone said, oh, we always do like that since the beginning. No. So we've covered a lot of ground, 6 stages, dozens of specific SOPs. The risk now is that this feels overwhelming. We need to see months and dedicated team just to write all this down. No, I want to push back that strongly. Really. SOPs do not need to be comprehensive before they deliver value. A one-page checklist for the pre-run review, completed and signed, will prevent more errors this month than a 200-page quality manual that didn't finish for another year. So what I mean here, start with the minimum viable SOP, and then from that, iterate. So the step 1 would be audit first. Before writing anything, map your current practice. Interview your 3 most experienced analysts. Where do they agree? Where does each person do something different? And that divergence is your priority SOP list. Then, for this implementation, the fastest path to SOP adoption is a template people actually use. A pre-run checklist in a shared folder, for example, a standard result plot configuration, a mesh quality report in a familiar format. These feel useful immediately because they are, okay? So the template before process. Then co-author with practitioners because SOPs written by management are not used, while the SOPs written by the engineers who do the work are followed. So identify your most respected technical leads and make them the co-author of your SOPs. Their credibility transfers to the document. Then you have the version control from day one. Your first SOP will not be your best SOP, okay? That is fine, and it is expected. What matters is that you can trace the evolution. What changes, when, and why. So it can be a SharePoint folder with version numbers and a changelog. It's enough. A sophisticated document management system is better, okay? It will come later. This step is embedded in onboarding. So the highest leverage moment for SOP assumption is onboarding. And I say that because I observe that every time. A new engineer who learns the SOP at the default, as the default way, of working, will follow it naturally. An experienced engineer asked to change their habits will resist. It's clear. So build the SOPs into your technical onboarding curriculum from the start. And finally, in order to implement SOP in your organization, this step six is important. The lessons learned drive iteration. After every major project, just take time to run a 30-minute lesson learned session, specifically focused on the FEA process. What worked? What failed? What should the SOP say differently? As I said, it is iterative, okay? This cadence ensures your SOPs evolve with your experience. So, a quick show of hands in the chat. How many of you could implement at least one of these steps this week? I'm betting that most of you could do step 2, okay? A shared checklist template before Friday. So let me know in the chat how many of you could implement that, at least one of the steps, okay? I am curious to see. Don't be shy. So let's continue that. Mark said yes. Which step, Mark? Let us know. Which step do you think? Many people are answering. Mark said the third one. Okay, the engage your team. Yeah, you're right. This one is easy because you just need to communicate with them, and some people say 3, 1, 2, 3. Yeah, I can actually finish my first template, said Ryan. So you see, as I said, it's iterative. Okay, so you can start building something, and stage by stage, you will have something more and more robust. You're going to discuss with the team members, and you will improve. And based on that, you will have something on paper, something robust that you're going to share with all the members. Okay, you just need to follow a process, because building a model, it's iterative. You have to follow some defined step, but defining the SOP, it is the same. You need to go step by step. If you follow the steps, you will have something very robust, and you will improve significantly the quality of your simulations. This slide, it's a bonus slide, okay? And it might be the most practically useful one in the deck. I've distilled more than 20 years of reviewing other people's FEA work into 10 mistakes I see every time. Repeatedly, okay? Repeatedly, sorry. For every mistake, there is a specific SOP that prevents it. This is the payoff. Specific problems, specific solutions. Let's go through them. My favorite one, I started with that. The wrong unit system at model import. This is the most common silent error in FEA. The fix is a unit system SOP that mandates specification at project kickoff and checking at every import. One checkbox prevents a class of error that can invalidate an entire analysis. And believe me, I made these mistakes myself at the beginning of my career, especially when I moved from Europe in the international system to North America, where I work in the empirical system. The second error is the unverified material data from old models. Material cards propagate through an organization history like successive photocopies. Each generation a little less sharp, a little less traceable, until the original is unrecognizable, okay? The fix is simple. It is a centralized library where every entry is traced to its source. No source, no entry. Third one, over-constrained boundary conditions. Analysts add constraints because they are worried about rigid body motion, and they add too many. So at the end of the day, the model is over-constrained and the behavior is wrong. The fix is a rational requirement. Every constraint must be justified itself in writing. Okay, you cannot put a constraint without justify it. Okay, compared to the writing. The fourth one, no mesh convergence study. I know, convergence study takes time. I know. The schedule skill convergence study. The fix is to make the convergence study a gate. Results are not accepted without a signed convergence confirmation. Another typical error, the solver warnings ignored, okay, or unlocked. The warning messages are the solver telling you something unexpected is happening. The solver is talking with you with the log file, okay? Ignoring them is a professional negligence. The fix is mandatory adjudication. Every warning reviewed, documented, and dispositioned. Okay? It's simple. You open the log file, you read them, you understand them, and you make sure that it makes sense. And you move on. Another error, it is the acceptance criteria set after seeing results. This is the most intellectually honest mistakes on this list. It doesn't feel like a mistake. The fix is to enforce the sequence, criteria documented and approved in the analysis plan before the run. Also, the loads not traced to a source document. Where this 50 kilonewton load come from? If the analyst can't answer that question, in 30 seconds, the load is unverified. The fix is a load source field on every load definition in the analysis plan. Okay, you know where the loads come from, and you know if you define the loads, you know how the method you use in order to define them, and you document this method on the analysis plan. The eighth error is no free body diagram check post solve. The free body diagram checks takes 15 minutes and catches a significant portion of the major model errors. Okay, because it is by nature the best check to verify the load path. Okay, skipping it to save time is a false economy. Make it mandatory. The ninth error is an ambiguous result plot in the deliverable. A plot without a scale, without units, without a coordinate system reference in an interpretable image. For example, you see an image, okay, with vectors showing forces or displacement, stuff like that. Please display the coordinate system, okay? Make the coordinate system reference. The post-processing standard fixes this in one document, okay? And this is valid for all the extractions, the stress extraction, the strain extractions. You document the stresses. It is an average stress, von Mises principle. Be explicit, okay? The last error, common error, it is the analysis assumptions never documented. Every FEA contains every FEA contains assumptions. Some are significant, some are less significant, okay? None are dangerous as long as they are documented. The deliverable SOP requires an explicit assumption section in every report. And this section is big usually because we are making a lot of assumptions when we build a model, okay? So these sections need to be very detailed. So you see, building an SOP, it's a demanding task. It takes time. You have to use your best engineers in order to build that. But I can offer you some resources. FEA Academy exists to give engineers the deep, rigorous FEA training, mentoring, and coaching that most organizations don't have the time or resource to deliver internally. Here is what's available to you right now at the FEA Academy website. First, online courses. We have the practical basic FEA course in 20 hours, the practical nonlinear FEA course in 12 hours, and available soon, the model debugging in FEA. It will be an advanced course to help you verify, validate, and debug your model for linear and nonlinear analysis. We have also the mentoring and coaching program available for you. Okay, we have the monthly mentoring plans for individual engineers, but we have also the annual subscriptions for companies involving from 5 to 20 engineers. We have also the FEA Academy YouTube channel, FEA Mastery, and as I said, today's session will be available as a replay in 40 hours. We have plenty of videos, so here you can explore our comprehensive series of video tailored both for engineers and beginners and experienced engineers. So to stay updated, subscribe to the channel. And we have also free resources on the FEA Academy website, where I share some PDF, where I cover the good modeling practices, the fundamentals in mesh generation, the FEA theory in depth, the SOP starter kit will be available to download in PDF format after this session, and more. So all the resources are at the FEA Academy website. You have the link at the bottom of this slide. And the SOP starter kit is something I particularly recommend. Okay, if you want to start building the SOP in your organization and guide your organization, you will be able to use this document. On top of that, we can do mentoring together where I follow you and I make sure that you are on the good track in order to put that in place into your organization. Before to go to the Q&A session, I have 5 things that I want to take away. I want you to take away, okay, from today. 5 things. If you remember only 5 things from today. SOPs are not bureaucracy. They are engineering disciplines applied to processes. The same rigor you apply to your physics should apply to your method. Every stage at the FEA pipeline has specific failure modes that SOPs prevent. All 6 stages, not just the ones that feel risky. And it is the powerful of SOP. Consistency reduces errors, accelerates review, and builds client trust. These benefits are measurable and they compound over time. Start small, and the best SOP you will ever write is the one that gets used. A 1-page checklist, used consistently. It beats a 100-page manual that lives on the server. Okay? And finally, the best SOPs are written by the engineers who do the work. Give your most experienced people the authorship. Their ownership is what makes it real. Okay? So those takeaways are here to reveal that, yes, we build complex simulation. Those complex simulations, most of the time, they have a lot of errors. Small mistakes here and there, and it produces wrong results. By building a strong SOPs, you will completely remove those errors at every stage of the building process. So thank you for listening to me. And I know your time is your most constrained resource. And the fact that you've spent an hour here on this topic tells me you care about the quality of your work. So thank you very much, everyone. The SOP starter kit in PDF format will be available a few minutes after this live session on the FEA Academy website. I encourage you to download it today while the content of this session is fresh. If there is one action I'd ask you to commit to, okay, before you close your laptop today, identify the one SOP you will write or have written this week. It doesn't need to be comprehensive. It needs to exist. It will be a very good starting point. And believe me, if you do that, you will have an SOP in few weeks, maximum 1 month. If you need help, please contact me. I can guide you. I guided a lot of companies, a lot of organizations in my life through this process. So I am a very good resource for you. Thank you again for your time, and I hope to see you at the next FEA Academy event. Take care and bye-bye.